Okay, welcome to Hints for Your Lab with Dr. Green. Okay, so in your lab, sorry, let me turn that off. We have a question, right? And the question is pretty simple. What is the stoichiometric ratio, the mole ratio between hydrogen and oxygen that reacts to form water? And it's pretty easy to come up with a hypothesis for that because you can just balance the equation. And that's your hypothesis. Of course, you need to state it with error allowances preferably. All right. But I want to talk a little bit about the graph and kind of the nature of our data here. So let's say this is my graph. Now I want to put my independent variable on the x-axis, and on the y-axis I'm going to put the loudness rating. And maybe that goes from 1 to 5, for example. All right. And on the x-axis, though, I want to make this quantitative. I want to make this a scatter plot. I know it looks like you could do it as a bar graph, but I'm going to show you why I think a scatter plot is better. And all I'm going to do on here is I'm going to put volumes or volume of hydrogen. That way I can start with 0 because that's when we had pure oxygen and no hydrogen. And then I can just go up evenly 1, 2, 3, 4, 5, and 6. And these should be evenly spaced because I've got 1 through 6 volumes of hydrogen. Of course, when I had 6 volumes of hydrogen, that means I had 0 volume O2. All right. Now, let's just say that my data looked something like this. Like I had maybe it was like this. I'm not saying your data's going to look like this, but just hypothetically speaking. All right, and I'm going to put some error bars on here. Yeah, let's move this one down a little. Okay, now it seems pretty clear that in this case, the 3 volumes of hydrogen worked best, which was actually the 1-to-1 ratio. And again, I'm not saying that your data should look like this. I'm just throwing this out there as kind of a hypothetical situation. And I could justify that conclusion that the 3-to-3 or the 1-to-1 worked best because the error bars don't overlap here. That treatment is well above the next 2 highest right here. And there's no overlap in error, so I can be pretty sure that they are actually different, that the 3-to-3 is actually higher. Okay, so that would be good, but I want to talk just a little bit about why I think it's important that we have a quantitative x-axis here. And that is that how can I be sure that there wasn't some other ratio that would have been higher than these nice, clean, simple whole number ratios that I used? For example, we did a 0 to 6, a 1 to 5, a 2 to 4, a 3 to 3, and so on. But what if I had something like something that wouldn't come out exactly like that, like a 1.5 to 4.5, for example? Who's to say that a 1.5 to 4.5 wouldn't have been a better ratio? Well, it turns out we can draw a conclusion about that because we have a graph here. We have a trend. We have a quantitative trend with a quantitative x-axis, quantitative y-axis, and we can actually show that the trend itself seems to peak at that ratio. And so we can draw kind of a firmer conclusion because of that. we can say that we're pretty confident that the actual ratio was not somewhere in between one of our other treatments here. Okay. Now moving on to the explanation section, I just want to make a quick point about that. In the explanation section, we want to be sure to talk about limiting reactants, and you're going to have to mention the fact that we controlled for total moles. And I'm not going to tell you any more than that, but those two things are needed to correctly explain this in terms of specific chemical mechanisms, which is what we're looking for. In the importance section, what we're always looking for here really is the importance of the trend. And so let's apply that in this case. What I mean is, if we assume that this is true for all chemical reactions, that all chemical reactions will have a specific mole ratio, that is, that their reactants will react most efficiently in a specific mole ratio, then that has a much broader importance than if we try to apply this specifically to the reaction between hydrogen and oxygen. So let's kind of broaden this out and talk about the importance of specific or definite mole ratios in chemical reactions. All right, and that'll make it easier for you to expand, to make that important for everyday life or for in kind of a more real world or general application. All right, so good luck with that, folks.